So I think we can start. So welcome everybody to the Astromeeting seminar. It's a pleasure to have as a speaker today Luca di Mascolo from the University of Trieste. So I got the master degree in 2016 at the University of Roma Tor Vergata, and then the PhD degree at MPA in Gacchi in 2020, and then he moved to Trieste, and then he will soon move to Nice, where he got the PhD postdoc position, so congratulations. So he's an expert on protoclusters, clusters, and intracluster light. And today we'll talk about tracing the inception of the galactic cluster. So
thank you very, very much for the introduction. So yeah, I'm going to talk about like galaxy clusters and all this what we like to describe as the largest gravitationally bound objects in the universe. So galaxy clusters, we have to start with the definition, right, of what is a galaxy cluster, and beyond the gravitationally bound structure. So this is an image of a galaxy cluster. It's a composite one. We have of course the galaxies, composite clusters. But what I really like about this is despite the name, galaxies actually are a very minor part of a galaxy cluster. Most of the mass, of the baryonic mass, is actually in the form of this very diffuse and dilute gas, which is the intercluster medium. And for me, it kind of represents the gluing factor that's really connecting the cosmological aspect of galaxy cluster studies to galaxy evolution studies. And also, what I'm really interested into. Why I'm telling this? So the evolution of galaxy cluster, of course, is driven by cosmic accretion and mergers, and what happens by studying the just evolution structure, we can really understand how the universe evolved, and it's important for multiple aspects. So first of all, because since they're the very end of structure formation, of course they really are kind of a biased view on the evolution of the universe, and of course on the cosmological model. It's they host a huge amount of dark matter, of course, so it can really just provide us an observational means for testing different dark matter models. But then, of course, also represent kind of a large-scale environment for galaxy evolution. So we have, of course, galaxy evolved within the systems, and you're kind of in some sense, you're kind of in a small-scale universe, because when we really understand how environmental impact can influence the evolution of structures, and we are seeing this, what happens, it's a very energetic history. We have interaction between larger halos. We have interaction of the smaller galaxies with the largest halos here. But as I was mentioning, there's also something else. We once again intercluster medium. It's also important to just keep the slide. But I was saying it's important also because it really are the largest reservoir of this gas that we have in the universe, which means it's important for, first of all, studying the plasma itself. We reach energies that are not that we cannot obtain on Earth with laboratories. But of course, also really different regimes what we can get in terms of scales. And it's important, for example, understanding the interaction between gravitational effects on dark matter, for example, and the quantum medium itself. But why it's important to study this, of course, in redshift and in time, because we can really understand the evolution. And this is what has been done in the past. So this is a collection of the clusters that we're detecting in a large field surveys. You can see we basically go from redshift 0 roughly to redshift 2. And just before starting this, what's your definition of high redshift? So let's go let's raise hands. Below. Yes, exactly. So it's high redshift. How many of you is above 10? Redshift 10. Above 2. Above 1? Okay. Okay, roughly from
for us, 1, 2 is like
1, 2, 3.
It's enough, yeah.
Okay. Because I gave actually a talk at dawn, and yeah, I heard 12, come on. So for me, high redshift is actually redshift 2. Okay, so everything is beyond redshift 2. What's the reason? You can see it's it's kind of a gap, right, in this plot. So it's there are missing clusters there. This is not really, of course, the case. There are multiple reasons, and one of these is we don't have instrument for actually probing this region here. But it's also to astrophysical reason. So in general, like we like to call this the realm of photoclusters. So it's like a region where we actually have the formation of the first clusters that then emerge from the cosmic web, like around Redshift 2. But it's not like just important for clusters. It's most like a really embedded situation there, because we have the evolution of galaxies. And Redshift 2 is kind of a transitional epoch, because we have the peak in AGN activity, the peak in star formation, and at the same time, right, the emergence of intercluster medium. And we just move from very sparse densities of galaxies and then like really active galaxies to really passive, kind of really kind of relaxed system with a lot of intercluster medium in it. But the point is, like judging from the previous plot, right, we should observe like this emergence of intercluster medium, right, like at Redshift 2, and it shouldn't happen like abruptly. We should be like slow accretion, slow evolution of that. So together with the transition in galaxy evolution, we should also observe kind of like the first seeds of the intercluster medium. There should be, of course, stars, because we don't have fully virialized structures, but we can really move into practice from this very complex system with like the very first preheated seeds of intercluster medium to like the most massive one. We don't observe that though. We still have like a huge gap, Redshift 2, and there's someone entering. So what's the reason for that? There are, in my opinion, two motivations. So the first is actually an approach. So when you are Redshift 2, you kind of have two directions. You can actually move from higher Redshift to Redshift 2, and you have it. All the studies have been driven mostly by actually galaxy evolution perspective. And this, for example, like the case of the spiderweb photocluster, which actually the focus of this talk. This is a collection of all the works on this system for the past roughly 30 years. As you can see, there's been like a lot of activity on this, a lot of different perspectives. I don't want to get into the fine details of what's being like studied, but it's like a lot here. So, but we still basically miss a perspective on SEM that we only got actually this year, okay, after 2 years like of work. And this actually, it's really just telling us that most of the studies really focus on like understanding what the galaxies are doing. They're really getting an understanding of the environment that's just surrounding them. But there is another reason for that. It's not only because I think people like galaxies. Because intercluster medium studies have been mostly driven by X-ray observations. This is just once again a nice collection of pictures. You don't have to get into the details. But it's just basically what we have in terms of like high resolution observation of galaxy clusters. We move from understanding, for example, like the shocks, light shocks in clusters due to like the mergers of like 2 or more clusters. We have the interaction, for example, like AGN with the large scale environment, and the injection of a lot of like thermal energy and mechanical energy into the ICM. We have all the small scale perturbations that, for example, make cluster deviate from hydrostatic equilibrium, which is kind of the key assumption for using cluster for cosmology. And then also all the like low density and low temperature environments connecting into 2 clusters and kind of defining the cosmic web on our scales. We using theory for understanding all this, we really have got to a point of like a lot of advances in cluster studies, but all the systems are really, really low Redshift case, and talking about like here, like around 0.5 maximum. What happens when we move to high Redshift? Once again, my definition of high Redshift is Redshift 2. So this happens. It's not that nice as the previous image. And of course, to be totally fair, it's actually an amazing observation of like a Redshift 2 galaxy cluster. But the main limitation is that, of course, we cannot really get into the finer details of intercluster medium, and cannot really understand the physical properties really. Still, not breaking the observatory. So it's a really cool case here. What can we do? So the problem with X-ray observations is that they, as any astrophysical, of course, emission, suffers of cosmological dimming. The farther we go, the dimmer. There is a solution for that, which is called the Sinaitis-Lovich effect. I don't know if you ever saw a talk about the SZ effect, but we really like to show this image for some reason. But I think it's useful for just getting a bit of why the SZ is really important. So what happens basically, like we are inverse quantum scattering the CMB photons. Okay, basically the electrons are hotter than the CMB photons, just kicking the photons a little bit in energy and just up scattering them to higher frequencies. So what happens basically is a spectral distortion of the CMB, right, itself. Just think about it like, basically casting a shadow, right, on the screen that's always fixed in redshift. Like it's never moving, like always like 1100, meaning that actually the amplitude of the SD signal does not depend on redshift. So it's a really key important, like it's a really key thing because it means that we can basically probe the cosmic history just with no limit in redshift using the SD effect. Is that okay? Great. Of course, if you have questions, please stop me. I really prefer to just have a conversation here. What's measuring, like you see, is actually measuring like the integrated pressure of electrons, and this should be actually thermalized. Okay, so that's the important thing. The fact that we can really probe the thermal history of clusters and structure in general actually have been used in the past. This, for example, it's not really easy to see here. Yeah, let me just zoom in a little bit. Oops. Okay, I'm not zooming in, but all the signal points here. Basically, all these are clusters, individual clusters. So we just basically have the ability of mapping the position of clusters, just checking, and the spectral distortion. So there's like tiny variation in the CMB in the direction of a system. The thing I wanted to mention, though, and it's not moving again, is that unfortunately, past observations are really limited in resolution. So, for example, this is actually one of the standard observations we have. So I always like to play a game with this slide. Can you recognize the cluster? Which cluster is this one?
Yeah.
Absolutely, no. So this is not a star. High resolution star. So this actually is an observation of a very famous cluster by Planck, which is kind of like the golden standard for using SD observations for finding clusters. But of course, like we had a bit of advances in the past, and we had like two instruments. For example, we have the Gamma Cosmology Telescope. This is the same cluster, okay, but a high resolution, like an amazing resolution of 1.5 minutes. Can you recognize it? I mean, it's an amazing hint here. You can clearly see what's that, right? So, drum roll. So this is actually the bullet cluster. Okay, so this is really probably the most famous one, and the main point here is that it's really hard to understand what's going on in this system if you just use single-digit observations from this of the SD effect, and of course, like data from wide field surveys. There is a way for solving this. It is going for like ALMA. Probably don't have to introduce you to this. Just to let you understand how amazing it is. Remember, like that X-ray cluster at redshift of 2, with a bunch of photons. This is the same image, but in the SD, with like 1/7 of the integration time. And this study is led by Yoshiba Wamarai from ISO, the PhD student. And it's just amazing. Basically, we can really get into arc-second resolution information. And just basically what we did after we were constructing the entire pressure distribution of this redshift 2 system. So just to give you a better sense, this is actually the improvement that we're having in terms of like, it's not moving, it's moving now, from like Planck, as I showed before, moving to ALMA, and this actually is the upper limit in resolution we can achieve with ALMA. So we can really like probe the tiny scale and really have a complementary view, for example, like X-ray observations in terms of like resolution, but also in terms of like what we're actually probing. Of course, nothing comes for free. There is a problem, a huge issue with ALMA. Let's go back to my very beloved bullet cluster. So what happens if you just point ALMA towards like the system, and the first thing you can see is like the field of view is tiny, right? So we can only probe this very region, which is where we have the shock from. So where basically the shock waves propagating, we just actually study the energetics of this process. This is what we will get, which is, to me it looks amazing, but I can realize it's not that great. Let's just clean up a little bit, nice. It actually is the model that we can get. So it doesn't look like, what we could expect from here, right? Like we could expect some, homogeneous signal in this region, that kind of like a gradient. It's kind of like more like a strip. The thing is connected like how ALMA observe like galaxy clusters, we're just filtering like information. And the problem is like galaxy clusters are way larger than the scales are probed by ALMA. So just to give you kind of more quantitative idea, in red is the input profile we can expect from the pressure distribution of the galaxy cluster and the integrated, of course, pressure. And the yellow banana curves actually what we can measure really with ALMA. So we're just basically removing information on very large scales. So basically the idea, when you have like a step function, you just remove large scales, you start to have ringing around it, right? That's just it. So we have very, very, very like, very narrow range of scales that we can probe that can provide us information. Still, it's very high resolution. So what is the issue? So let's go a bit more with this. Everything condensate to this hole. So this is like a standard observation with ALMA. What we have is that like we have a lot of missing information from this part. There's like this tiny region here is where actually the SZ is important because it's like really extended in terms of like scales. And so we're just basically removing out information. So we're actually losing, the possibility of like training our scale structure. The other issue is that since, for example, like ALMA was optimized for studying small structures and like small sources, we don't have the tools actually for really getting and reconstructing the signal, which is a huge limitation. And the other problem, and this is mostly connected to photocluster realm, is that since we don't have many observations at very high redshift, we don't have models for describing what the signal should be and like for extrapolating into our observation. So how does it convert like to actually a real photocluster? So let me go back to this. This is Padua photocluster. Give you a bit of context. We're talking about like redshift 2.16. This is probably the best studied photocluster we can find in the literature. When we just point like an interferometer towards like the system, what we see is not the SZ effect, because actually, as you can see here, we have like a radio source, just like traced by this red signaling in the map and these red contours. It's super bright. So one of the ways of finding photocluster is actually checking for very bright AGN and very bright radio galaxies. It's kind of like they're generally called like radio beacons, because just can really just guide us in like finding over densities. And this is not like a graphic representation. This is actually an actual plot of like basically the signal you have here, and there is the SZ actually in here. So like show, let's zoom in. It's a tiny fraction of the overall signal. So basically what we have is that we have basically like a strong, very bright radio galaxy entirely contaminating the signal from the SZ, and so from the forming intercluster medium. When I talk about like contamination, so this is actually an important point that I missed before. We're actually observing at 90 gigahertz for this set of data, meaning that the SZ looks like a decrement, so kind of like a missing flux. So we just point subscript in the direction of a cluster at this frequency, we'll see basically like negative signal, so kind of like an absorption, but in continuum, and there is no other astrophysical source and astrophysical part that can produce an absorption in like a continuum, like a broadband. Which is really cool because we can really understand that that's actually the effect. But of course, it means that if you have a very bright positive source, you can completely entirely infill, of course, the signal from the structure. I mentioned before, like we have missing tools, right, for modeling this. Let's just do huge leap forward, and we have the tools now. We know how to subtract this, like cleanly. What happens when we do this is we obtain this plot. Just to get you a bit through here. What we have is like basically the amplitude of the Fourier modes. Okay, I will get back to this in a second. And when moving in this direction, so larger UV distances means like larger baselines, so larger Fourier modes, we actually move to smaller scales. Okay, when you move like to this part, we actually move to larger scales. I'm not talking about radii, just talking about scales, because what happens like is the radio interferometer is actually measuring in Fourier space. So just measuring the power at each Fourier mode. What we can do then is understand how much power there is in any Fourier mode. We can do this radially just to simplify, of course, the visualization. What you see that since we expect to see a negative contribution to the total flux of the region, we should expect, of course, a decaying curve when we move to larger scales. Because of course we're talking about a very diffuse system, right? So larger scales, larger negative signal. And indeed, this is what we get. After subtracting the information from the radio galaxy, this is really the decay due to the presence of the Z effect. And this is for comparison, what we should expect, of course, in the presence of no Z effect at all. And this is the result. I could just leave and that's it. Why it's important, so basically this is just confirming, just part of the observational confirmation of theory that we had for the past 30 years. So the spider of the galaxy, and at the center of the spider of the protocluster, is a strongly self-forming system, and one of the reasons for justifying this is that we have a huge inflow of gas from the surrounding that will require, of course, a huge halo of gas. So hot gas just condensating and precipitating in. The other thing is that we have also observations of Faraday rotation. They're basically just telling us that a huge amount of polarization in the radio galaxy that will require a huge amount of diffuse hot gas in the surrounding. And then of course we have simulations that predicted this for a while now, but we really had no opportunity for just testing the observation before this observation. So yeah, as I mentioned, everything works. Woo! That's not the case, actually. We have a lot of issues still. First, it's a protocluster, meaning that first we have galaxies in there. So what we can do is just to take all the galaxies and compute the dynamical mass for the system. What we see is that the expectation for the mass we get from just the motion of galaxies, it's way larger, than what we get from the SZ signal, so for a similar mass. This is because, of course, there is a relation between the integrated SZ signal and mass of a system, and there is something wrong here. One of the possibilities is that this relation is not really working up to ratio 2, or beyond, and actually it's kind of supported by simulations. You can see here basically the what's governing the SZ scaling, mass SZ scaling, driven by self-similarity of structures. So when we move to higher and higher redshift, we see a deviation and departure from the expectation for full self-similarity. So that could be the case, of course, meaning that we cannot really use the models that we actually have on the modern system to describe high redshift structures. But maybe that's not really the case. This is basically a comparison of the masses that we obtain for different analytical models compared to the dynamical mass estimate that I showed before. And except for these two models here, that are actually the yellow ones, all of these actually have deviation from similarity integrated in terms of parametric characterization. So maybe then that's not really the case. Maybe there's something more. There could be an astrophysical reason, because of course these are forming structures, right? And clusters form through accretion and mergers, meaning that it could be really disturbed system. If it's really disturbed, there might be actually a contribution to the overall pressure that is not thermal. As I mentioned before, the SZ is actually measuring the integrated thermal pressure of a structure. And if you have turbulence, for example, they will lower the integrated signal, but will still have a lot of pressure in it. For example, magnetic fields, right? What we see once again from simulations that we have a huge amount, of course, turbulent motion and non-thermal pressure support in the structures. So that could be the case, is that as the signal is just lower for compared to so the mass is correct. It's just that we're just measuring not enough to see. There could be a deviation from thermalization. So the thing is, we see that, for example, a redshift 2, once again, simulations, we don't have full thermalization of the hot gas. So we have a lot of contribution from what's defined like warm. This, of course, is not going to contribute in the same way as for virialise systems to the overall SZ signal. So the deviation will actually be into the composition of the actual halo we have. There is another point. Mergers are really complicated processes. Because what happens, like, when you just have two clusters merging, first dark matter will increase naturally, like, the mass, the structure by just simply summing mass first. But the SC signal is not like really following that evolution. So what we see is that actually the SC is kind of lagging behind compared to the mass evolution, in terms of like temporal, like, steps. So we might be observing this system in a phase that actually have a lower SC signal compared to the total mass, simply because of the transitioning phase. Of course, it's a protocluster once again, and it might be actually really catching this specific like evolutionary step in galaxy clusters. And then the last problem, I swear, we have limited information. So this is basically the bands that we use for measuring the SC signal. What we have here is a collection of SC signals, because I just always thought like in a singular way, actually, depending on the specific distribution of velocity of electrons, you might have different SC effects. So the one I always talk about like during this talk is this yellow curve, which is the thermal SC that is generated by the thermal bath of electrons in a structure. But for example, if we have very hot systems, it might have deviations to this yellow curve that are just introduced because like we just have relativistic effects. So we just change the net result. For example, like here we see that we lower the oil signal. We have a contribution from kinetic SC, which is basically due to the bulk motion of structures inside like a system or the system itself compared to the CMB frame, which is a really cool way for measuring actually peculiar velocities. But of course, this can kind of contaminate or like vary the overall SC we measure. And the last one is kind of a bit into the fancy part, like purely relativistic. We have a very bright AGN inside a real galaxy that might be injecting cosmic rays, and this could actually remove some thermal component and actually introduce a relativistic term. Okay. The thing is, since we're here, we cannot really distinguish this, and we are fully degenerate. So it might be we have actually an observational bias. So how to check all this? Once again, let's go to and check simulations. So what I did is taking a set of cosmological simulations, the Dianoga set, zoom in, very high resolution, and to basically resimulate the observation itself, taking into account all the different contributions that we can get. This is just a nice image before going to this one. So this is basically the profiles that we obtain after creating mock observations. So resimulating the entire observation for each of the cluster in the system. We're talking about 27 systems at redshift 0 with all the different progenitors for redshift 2. And these are color-coded with the mass. So the idea is that, roughly speaking, and we don't have an exact match, because of course the idea was not to obtain a kind of simulated between all the spider color cluster, but just to have a rough comparison, is that the mass range that fits the data is actually consistent with what we get from the analytical model. So maybe there's something more that is related more to the dynamical state of the system. It's impacting the dispersion measurement, of course, of the mass. And the Z instead is kind of making sense. So there might be something more, and maybe everything is kind of subsimilar already redshift 2. So this kind of cross-check that everything is working, and we're kind of getting the rough correct answer. So, and then I'm almost done. But before concluding, I intentionally did not show any image of this effect. There was there's a reason for that, because actually all the analyses were performed in Fourier space. Since we have, of course, the observations are basically taking power Fourier modes, it's really important to really do this directly on the visibilities, on the Fourier modes. But then, of course, we can image stuff. Once again, this is the spiderweb galaxy. What happens is that if we add on top of this, once again, it's an HST image that's superimposed to the VLA image tracing in the radio galaxy. And we add the LC effect. This is what we get. So we can start to see this kind of an offset between the bulk distribution of the Z and the radio galaxy. It is centered here. This is the nucleus. Don't take the small scale features as real. They're probably dominated by noise. What's important here is the bulk distribution, kind of the large scale pattern. Let's add another thing, which is Lyman alpha. We see it's kind of similar symmetry, but in the other direction compared to the ICM. Let's add another thing, which is the CO emission. So what's really telling us this multi-wavelength perspective is that dynamical processes, once again, might be really driving the evolution of the core. And in particular, what might be happening is that we have dynamical structure here, just with the ICM kind of lagging behind the motion, or just preceding the motion of the galaxy itself. And this galaxy has like radio jets with very different observational properties. It's kind of like an F1, F2. So this really, what might be telling us that actually there's like a different environmental impact on the two sides, with this one actually having a stronger pressure, feeling a stronger pressure, stronger intensity, probably due to like a higher density region, because of course we also have the Lyman alpha block. But then it might be actually like effect of motion itself, and like combination with the shock heating of the structure, it might be creating this very asymmetric morphology. And finally, of course, we also have the CO. It's kind of like extending in the same direction as in the SZ, maybe telling us that there is a bit of, I forgot to have this, a bit of motion. Sorry, this is what's not moving. Of the entire structure. This is a bit like, so like a bit of a naive interpretation, because the problem is that we don't have any data that could really support this dynamical like formation of the core of this photocluster. But it just really showed that actually putting together like a lot of multiple perspectives, like a multi-phase gas and of course a multi-frequency, can tell us a bit more about like the galaxy gas formation. And kind of like a bit of Easter egg before concluding, there is a missing signal here. So we don't see any SZ in this direction here. And we also have X-ray observations. We don't see any X-ray observation in this direction. It could be, and once again, just take a could here, that we just have like seen like an inflation of a huge bubble in the SEM due to like the radio jet itself. And here is where like the relativistic term might be really important, the one I mentioned before, that deviating like the Z in the direction. Once again, we need more data, so hopefully we'll get this in the future. But just to wrap up, so the Z allowed us to really get us into understanding like the information about ICM and just getting like a first glance of this. And once again, demonstrated that the SZ could be used for tracing and thermal history of the universe with, once again, no limit basically in the redshift that we can reach. And then, of course, that multi-phase, multi-observations, and multi-wavelength studies is really important, because it can tell us that there's like a lot of disturbance in the cores and just not simply virialized system that's just evolving. What's missing entirely is, first of all, understanding how the AGN is actually impacting like the structure in general. And then, of course, also when we have a transition from the multi-phase situation we see here to what is actually a real cluster, which is mostly hot gas and a bit of like the rest. This actually on the right is an image from these press release we got on this. And I don't know, do I have any time left? I can go on. So what is important in a general broader context is that in the future we're going to have more SZ facilities. It's just a prediction, for example, of what we will get. We're like CMB-S4, for example, or CMB-HD. It's going to be the next generation CMB telescopes. But unfortunately, the spider web is sitting here, so we won't see that. But like this is where basically we're going to extend our observations, and so it's important to like build like a model for this. And the reason why I'm mentioning it is because I wanted to do a bit of advertisement together with this. I'm also working, and we're working for developing the science case for Atlas. We're going to be a next generation facility. This is the Gamma Large Aperture Submillimeter Telescope. The idea is to build like a 50-meter telescope. This will complement ALMA on the large scale side, but also on the field of view. Talking about roughly 1-2 degrees square of instantaneous field of view. And it's going to be like a really, really fast mapping machine. With the idea of also getting into like the spectral mapping. So just to have like a complete and quick redshift and wide field survey machine. This is important for like other cluster studies, of course. I mean, I'm super excited about it, but please ask me if you're interested, like, getting a bit into mapping, from the local environment, like, what we have running into like a very high redshift universe. And we're going to have a conference about this in May. So, if you're interested in this science, if you're interested in what we can achieve with a high resolution, high sensitivity facility, this is awesome. And with this, I'm done, and I'm really happy to answer any questions if there is any.